Snow muffled the sounds of the resort as music and laughter leaked through the walls, but inside the crowded room his attention stayed fixed on the uneven sums of nuclear physics. Every beta decay spectrum he had seen showed missing energy, as if nature quietly siphoned off a share that no detector registered. The law of energy conservation, the backbone of mechanics and electromagnetism alike, seemed to falter inside the atomic nucleus. In his letter, addressed to the radioactive ladies and gentlemen studying nuclear decay, he laid out a hypothesis that clung to the mathematical structure of the problem. If the electron and the recoiling nucleus did not carry all the measured energy and momentum, a third particle had to share the load. It had to be light, carry no electric charge, and leave no mark on photographic plates or ionization chambers. Only then could every equation close cleanly again. He described the proposal as a desperate remedy, aware that existing instruments had almost no chance of catching such a fugitive. Theoretical decay curves, however, straightened when the invisible particle entered the calculation, and angular momentum and statistics fell back into place. A scientist known for dismantling speculative ideas now leaned on the authority of conservation laws, allowing the equations themselves to insist that something unseen must have slipped away with each beta ray. Cloud chambers flickered with thin white tracks where charged particles passed, but in beta decay the evidence refused to line up. Radioactive nuclei hurled out electrons whose energies filled a smooth, continuous band instead of a sharp, fixed value. Each decay seemed to cheat the bookkeepers of physics. When experimenters added the mass of the original nucleus, the mass of the daughter, and the energy of the emitted electron, the totals wandered unpredictably from event to event. Physicists laid the equations of energy and momentum conservation beside the jagged experimental curves. Every familiar term sat in place, yet the algebra failed to match the measured spectra. Inside lecture halls, chalk scraped across blackboards as Enrico Fermi, Niels Bohr and others argued over what these stubborn discrepancies implied. Some suggested that energy conservation might only hold statistically, that deep within the atomic nucleus, nature might quietly suspend one of its strictest rules. Each new measurement tightened the vice, improved detectors, narrowed experimental errors, but the missing energy did not disappear. It piled up as a glaring absence on every graph. The nucleus recoiled, the electrons sped away, and still the sums fell short. The data accused no obvious culprit. Faced with either abandoning a foundational law or adding something unseen to the ledger, theorists were driven toward a radical possibility. An invisible particle silently carried off the deficit. In a cramped office at the University of Rome, sheets of paper had covered the desk where Enrico Fermi worked through the puzzle of beta decay. Reports of energies that never quite added up had reached him from laboratories across Europe. He treated Wolfgang Pauli's speculative neutral particle not as an odd suggestion, but as a necessary element of a new interaction. Chalk dust clung to the blackboard while he rearranged symbols, searching for a consistent description of radioactive change. Fermi wrote an interaction term that joined four particles at a single point, a proton and a neutron-like partner on one side, an electron and an elusive neutral companion on the other. His expressions balanced energy, momentum, and angular momentum with mathematical precision. Colleagues watched him translate Pauli's ghostly entity into a participant in what he now called the weak force. In discussions and letters, the hypothetical particle acquired a clearer identity, even as no instrument had yet registered its presence. To distinguish it from James Chadwick's massive neutron, collaborators such as Edoardo Amaldi later referred to Fermi's particle as the neutrino, the little neutral one of his playful Italian. The equations fixed its role. They yielded detailed curves for electron energies in beta decay, specific emission probabilities, and expected decay rates for different nuclei. Calculations showed how often the unseen neutrino should emerge from radioactive atoms, assigning it a place in nature long before any detector could confirm that it had passed by. In quiet lecture halls and crowded conference rooms, diagrams of atoms and dense slabs of matter filled blackboards. Physicists calculated how often a neutrino should collide with anything at all and found an answer that bordered on the absurd: almost never. Thought experiments stretched sheets of hypothetical lead across light years. Yet the equations showed that most neutrinos would pass through untouched. The particle remained practically ghost-like, present in formulas but absent in every instrument. Animations and sketches traced torrents of neutrinos rushing outward from the nuclear reactions inside the Sun. Arrows pierced the orbit of Earth, swept through oceans, mountains, and metal as if they were empty space. Detectors seemed almost irrelevant against such indifference. In laboratories, engineers and theorists weighed the limits of their Geiger counters and cloud chambers, while the numbers on paper insisted that trillions of these particles passed unnoticed through each human body every second. Skeptical voices grew louder in discussions and published papers. Some senior researchers argued that a particle so elusive bordered on metaphysics, useful only as a temporary trick to balance energy books in beta decay. Yet the success of Fermi's theory left little room for alternatives. Hans Bethe and others folded neutrinos into models of stellar furnaces, showing how they carried energy from the Sun's core. In their calculations, the invisible particle already shaped the life of stars. Barbed wire and armed guards ringed the Savannah River plant, where heavy concrete walls muffled the steady rumble of nuclear reactors. In one corner of this secretive complex, Clyde Cowan and Frederick Reines stood among cables, pumps and shielding blocks, assembling an apparatus few believed would work. They aimed to detect neutrinos, particles that had slipped untouched through mountains, detectors and doubt for decades, yet poured invisibly from the reactor core in unimaginable numbers. Their detector rested like a buried vessel, a large tank of water laced with cadmium chloride, hidden beneath thick layers of shielding to dampen stray radiation. Photomultiplier tubes, their glass faces pressed against the darkness, waited to amplify the faintest glimmer of light. Diagrams on nearby chalkboards showed the hoped-for encounter: an anti-neutrino striking a proton, producing a positron and a neutron, each leaving its own timed imprint inside the silent volume of liquid. The positron's brief life ended in a flash as it annihilated with an electron, sending out gamma rays that triggered an initial burst of light in the tank. Microseconds later, the neutron slowed and was captured by a cadmium nucleus, releasing another set of gamma rays and a second flash. Months of counting and subtracting backgrounds yielded a small but unmistakable surplus of these paired signals. In 1956, the neutrino first proposed by Wolfgang Pauli stood revealed as a detected reality. In the late 1940s and 1950s, discussions in seminar rooms circled around a new conviction. The equations themselves carried clues to unseen matter. Quantum field theory spread from dense textbooks onto crowded chalkboards, where lines and loops encoded the behavior of particles and forces. Conservation of energy, momentum and charge ruled like strict bookkeepers. Whenever a process seemed to violate these rules, theorists added fields and particles to restore order, trusting logic before observation. Symmetry principles rose from mathematical curiosities to organizing laws of nature. Symbols like SU2 and SU3 appeared above diagrams of scattering events, capturing patterns in decay rates and cross-sections, At Brookhaven and other laboratories, detectors recorded tracks and flashes, while upstairs, calculations grouped particles into elegant multiplets. The neutrino's earlier success lingered as evidence that invisible actors could be real. If a symmetry demanded partners, theorists assumed those partners existed, even when detectors remained silent. By the early 1960s, Murray-Gell-Mann's quark model pushed this attitude further. Using SU3 symmetry, he arranged hadrons into neat families whose regular spacings suggested hidden constituents with fractional charge. No free quark appeared in any bubble chamber photograph, yet the algebra predicted entire sets of particles, including ones not yet seen. Down long accelerator tunnels at places like CERN, beams were tuned to test these patterns, while the chalkboard equations already treated quarks as indispensable building blocks. In the early 1960s, blackboards in Brussels, Edinburgh and London filled with symbols that challenged the simple picture of massless fields and perfect symmetry. Quantum field theories of the weak and electromagnetic forces demanded gauge symmetry, yet experiments showed heavy W and Z bosons must exist if the weak force was short-ranged. The photon stayed massless, but no consistent set of equations yet explained how some force carriers could acquire mass without destroying the symmetry at the heart of the theory. Calculations of spontaneous symmetry breaking offered a clue. A field with a non-zero value in empty space could tilt the energy landscape, forcing the vacuum into a particular orientation. But every attempt generated an extra prediction, a massless excitation, the Goldstone boson that should have appeared in detectors and had not. On paper, the unwanted mode slipped inevitably from the mathematics, an apparently unavoidable byproduct of breaking continuous symmetries in quantum fields. The key realization emerged in 1964 as theorists applied symmetry breaking to gauge theories. The troublesome Goldstone mode did not remain as a separate observable particle. Instead, it was absorbed into the gauge fields themselves, providing the missing degrees of freedom that endowed the W and Z bosons with mass. The equations then left behind one new ingredient, a massive scalar excitation of the field-filling space, a Higgs boson whose existence followed directly from the structure of the Lagrangian. In control rooms and detector halls from SLAC to Fermilab and CERN, screens and printouts had traced the growing authority of the Standard Model. Collisions had revealed the charm quark and then the bottom quark, each appearing at masses and production rates laid out by the equations years before. Jets of hadrons had exposed the presence of gluons, the carriers of the strong force. With every successful prediction, the abstract symmetry structure of the theory had taken on the weight of observed reality. In 1983, in caverns beneath the Swiss-French border, the superproton synchrotron drove protons and antiprotons into head-on collisions, and large detectors registered showers of particles. Physicists sifted through transverse momentum distributions and missing energy signatures until unmistakable peaks emerged. They corresponded to the W and Z bosons, with masses matching those calculated from electroweak theory that relied on the Higgs mechanism. The weak and electromagnetic forces had unified in the data, yet the Higgs boson itself remained conspicuously absent. In seminar rooms, blackboards filled with Feynman diagrams and dense integrals as theorists tested how far the equations could be pushed. Radiative corrections grew uncontrollably without some Higgs-like particle to tame them, threatening the unitarity and stability of the electroweak sector at high energies. Alternatives circulated: technicolor dynamics, composite Higgs constructs, more elaborate symmetries. Still, the mathematics kept circling back to a missing scalar boson, woven mathematically into the mechanism that granted mass to the W and Z, yet stubbornly unseen. Deep beneath the fields, straddling the Franco-Swiss border, the circular tunnel stretched for 27 kilometers, an underground ring of concrete and steel carved with millimeter precision. Crews installed superconducting magnets, each segment aligned to guide protons along nearly light-speed orbits. On the surface, control rooms filled with racks of electronics and cooling systems hummed. Every component had been specified to reach energies where a Higgs boson, if it existed, might briefly appear in the collisions. Across the Atlantic, archival footage showed hearings where officials argued over the superconducting super collider, a project that promised even higher energies under the plains of Texas. Diagrams of its proposed 87-kilometer ring contrasted with budget spreadsheets and skeptical questioning. Some physicists warned that cancelling it would slow the hunt for the Higgs. Others accepted that political priorities had shifted, leaving Europe's machine and the calculations that guided it as the likeliest path forward. Inside CERN, the Atlas and CMS halls rose around detector cores larger than cathedral naves. Engineers bolted together calorimeters, tracking layers, and superconducting solenoids, each calibrated to recognize fleeting traces of Higgs decays. Software teams tuned algorithms to sift through billions of proton collisions, searching for pairs of photons or Z and W bosons with telltale energies. Plots of predicted cross-sections and branching ratios lay open on desks, turning abstract equations into hardware and code. In the packed CERN auditorium in July 2012, rows of physicists leaned forward as the final slides appeared on the screen. The Atlas and CMS collaborations, working independently, reported a new resonance near 125 giga-electronvolts. On the mass plots, a narrow bump rose above the modelled background, its statistical significance climbing beyond the 5 sigma threshold. The patterns of decay into photon pairs, into Z bosons, into W bosons matched the signatures long calculated for the Higgs field's quantum excitation. In recorded interviews, Peter Higgs lowered his gaze, his voice unsteady, as he recalled scribbling the symmetry-breaking equations in the 1960s, never certain they described anything real. François Englert spoke of parallel efforts, where gauge symmetries demanded a mechanism to give particles mass without destroying mathematical consistency. In 2012, as applause filled the hall, those abstract symmetry requirements and renormalizable terms in the standard model, Lagrangian, appeared anchored to a particle that deposited energy in silicon detectors beneath the Swiss-French border. The vindication of the Higgs mechanism echoed earlier episodes. In 1930, Wolfgang Pauli's letter proposed a neutral, nearly massless particle to rescue conservation of energy and angular momentum in beta decay, years before Clyde Cowan and Frederick Reiners captured reactor antineutrinos in tanks of scintillating liquid. From neutrinos to the Higgs boson, equations constrained by symmetry and conservation laws repeatedly indicated missing pieces. Today, the same logic guided models of dark matter and right-handed neutrinos, sketching particles that still passed silently through detectors.